The broadcast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, good morning, or whatever time it is for each one of you. Welcome. This is Krishna Vidula here, and I'm going to make myself the presenter and introduce our speaker for today. So we have with us Dr. Kshitij Jarath, and this is the fourth webinar in the Research and Engineering, UMass Lowell Research and Engineering webinar series. The primary objective of this webinar series is to make you all, whoever is interested, familiar with some of the research, exciting work that is going on at UMass Lowell, which is my own home institution. As most of you know, I'm a faculty member here. So we would like to let people know about the exciting things happening in this corner of the world. And in case some of you are interested in collaborating or sending students over, it's a good opportunity for you to learn more about what we do. So today's topic is grand challenges and complex systems, and in particular with applications in robotic swarms and autonomous vehicles. Dr. Kshitij Jarath, as you can see from his photograph, handsome photograph here, he's a mechanical engineering department. He's an assistant professor in the Department of Mechanical Engineering at UMass Lowell. Prior to joining UMass Lowell, he was at Washington State University as a faculty member, and then before that he was a postdoctoral scholar at Penn State University in the Department of Aerospace Engineering. He received his master's and PhDs in mechanical engineering as well as a master's in electrical engineering from Penn State. His work spans several research areas related to cyber physical systems, robotics, instrumentation, and algorithm development, with specific interest in controlling global patterns emerging from local interactions in large-scale systems. He has used his expertise in control theory and statistical mechanics towards projects related to self-organized traffic jams, influencing robotic swarms, reliability of large-scale systems, characterization of sensor systems, and ground mitigation, human detection, and vehicle trafficking algorithms. His current work is focused on identifying the conditions that increase the observability of emergent patterns in multi-agent systems such as robotic swarms and human societies, and in developing local controllers for robots to meet global swarm objectives using virtual reality to enable human control of robotic swarms and determining the impact of self-driving vehicles on self-organizing traffic jams. So very impressive, and I'm sure we're all looking forward to your presentation, Kshitij. So I'm going to make you the presenter, and you will be on. And while you're doing that, you'll have to click show my screen, and let me remind the audience that feel free to text messages while the presentation is going on. If there's sufficient number of questions, I will stop in the middle and read them out. Otherwise, we'll wait till the end and address whatever comments or questions that show up. So over to you, Kshitij.
Thank you, Krishna, and hello, everyone. I'll just get started. So I always like to present my work in a split fashion. Basically, today we're all so busy with our lives, sometimes we miss out what the big picture is. So in the first part of my talk, I'll be talking about the grand challenges in complex systems theory. What is it exactly that we are essentially trying to focus on in my research lab? And then I'll talk about specific applications related to robotic swarms and connected autonomous vehicles or self-driving cars, as we begin to call them. But before we start off with any of this, the essential question is, what is a complex system, right? Some of us might know what a complex system is, some of us might not, but it always helps to, like I said, step back and think about this. So what exactly characterizes a complex system? So over here, we have a video of a flock of birds. And we can clearly see that this is an example of a complex system, a complex self-organizing system. And one of the things that we see immediately is that it's a distributed system with a really large number of agents. There are maybe tens of thousands of birds flying around here in a flock. Another thing that we maybe do not explicitly notice is that it has localized interagent nonlinear interactions. So the birds are interacting with one another, but they are nonlinear in nature. And finally, what we saw throughout the video was we could see a global spatiotemporal pattern. So we could see a pattern in space and time, which standing on the ground we could probably see, but maybe a bird that's flying in the flock itself cannot see that global pattern because its view is very limited. So by stepping back and looking at it from a different scale, a different spatial scale, or a different time scale, we are able to see these patterns. And if we stop for a moment and think about it, these patterns are everywhere in this world. So many complex systems exhibit this kind of complex collective emergent behavior, where the behavior rises from individual particles interacting in a nonlinear way, and we see a global pattern in space or time. So physical systems like snowflakes, no one is essentially telling a water molecule to bond together in a specific fashion. But when the temperature is really low, we begin to see these beautiful patterns in snowflakes. So this is an emergent property. There is nothing written in the behavior of an individual, a single water molecule, that would lead to generation of this kind of pattern. It's the interaction between the water molecules, the nonlinear interaction between the water molecules, that leads to this kind of emergent behavior. So we see this in physical systems. We see the same kind of behavior in biological systems, and we just saw a video of that. We see social systems and the economy also behave in this kind of fashion. We see emergent rise and fall in how the stock market behaves. We see trends in how human societies behave. So this kind of behavior is actually everywhere. And we also see this in technological systems. So if a single substation in a power grid fails, that might increase the load on the neighboring substations. And if that load is too high, then those substations might also fail. And this kind of interactive behavior essentially leads to a cascading blackout, of which we have seen a few, thankfully not too many. But it's important to basically understand these global scale patterns and how to understand how these dynamics evolve and how to control them in a global connected society. So the vision of my research lab is essentially to understand the collective emergent dynamics of our world and essentially to influence their behavior with minimal intervention. So in that regard, we're going to focus on two applications. We're going to focus on autonomous vehicles or self-driving vehicles in one part of the talk, and we're going to talk on focus on robotic swarms in another part of the talk. But like I mentioned, it's always important to have a general understanding, a broad understanding of what are the major challenges that essentially face the study of complex systems. So in our research lab, we have identified 6 different challenges. And the first one is quantifying and classifying complex systems. So on the left, the image that you see is essentially a satellite image, and we see congestion, traffic congestion, essentially. And the idea is does traffic congestion, do the dynamics of traffic congestion essentially, are they similar to the same as the image on the right, where we have a bunch of ants that are possibly headed towards their nest, right? If we are able to look at 2 really different kinds of systems and say these are potentially identical, so they maybe belong to a universal class, then what we can do is use the same tools that we use for, let's say, studying ants, and use them to understand traffic congestion. So this makes the problems that we face very tractable, and also gives us a big picture overview of, okay, system 1 and system 2 and system 3 are identical, and we can basically use the same set of tools to study them. So that actually alleviates some of the pressure on looking at developing different tools for these different kinds of systems, which at the root are essentially identical. So that's the first challenge, to be able to quantify and classify these complex systems. Within a complex system, a second challenge is to identify what the macro state is. So if some of you are familiar with state space modeling, when we do system dynamics or control theory, if you look at this entire bird flock, right, there might be, let's say, 1,000 birds in there. If you want to identify the state of a single bird, that might be position and velocity in, let's say, X, Y, and Z directions. So that's 6 states for every bird. And if you've got 1,000 birds, that's 6,000 states. Now, these kinds of problems become extremely difficult to handle because of the large dimensionality. So what would be really good is we as humans can stand back and say, okay, I see the swarm moving in a specific direction. Maybe a minute from now, it's going to be headed north or headed south based on what we observe. So instead of looking at 6,000 states, what we are essentially doing is we are looking at a macro state, so maybe a mean of the locations of the birds and the mean velocity of the birds in the flock. But that may not always be the best quantity or variable to use. The mean position and the mean velocity may not always be the best thing to use to describe the flock. That is why identifying or figuring out what the macro state is and tracking that macro state is an important second challenge. The third challenge is top-down control of complex systems. So let's say we have an understanding of what we want the global pattern to be. So let's say we want the stock market to rise. What should the interactions between individual companies be so that this rise happens? So we know what the global pattern is, but what should the local rules be in order to figure out, in order to get that rise in the global pattern? The fourth challenge is the inverse problem of this, where we know the local rules. So we know how the individual molecules of water, let's say, interact, but can we predict what kind of global pattern will form? As we've probably all heard that no two snowflakes are alike, but at the bottom, at the very bottom, the interactions between the molecules, water molecules, are essentially identical. So how can we basically predict what kind of emergent behavior will happen? The fifth challenge is essentially looking at an agent or trying to figure out which agents are influential. So where can a certain, let's say again in this example of a bird flock, where can a bird essentially make some maneuvers that could change the direction of the entire flock? So if the bird is present in this small yellow circle that I've drawn on the left, maybe it is not going to have a big impact on the entire direction of the flock. If it's in the center, in one of the bottom right circles that I've drawn, again, there are so many birds around it, maybe it does not have the maneuvering room to basically do anything. So maybe that is not going to be influential. So basically what we're trying to do, and then the third circle over there, it's towards the edge, but it's not really at the extreme edge. Maybe there it can have an impact on how to change the direction of the flock. And this becomes important when we start thinking about how to influence the emergent behavior in a complex system. The final challenge is actually quite philosophical, and I haven't gotten to it yet, is the direction of causality across scales. So if we think about us even as individual humans in a society, does our behavior affect the global dynamics? Does our behavior, the actions we take, impact the society? Or is it the society's dynamics that actually affect our individual behavior, right? And this is a very important question to answer, especially if you're thinking about how to influence the emergent behavior of a complex system. So just to step back and have a look at all those challenges, these are the 6 major challenges that we have identified in our research lab that we are trying to address. And what we'll do now is basically see how each of these challenges are being addressed with regards to specific applications in robotic systems, in robotic swarms, and in connected autonomous vehicles. So let's first take up robotic swarms and see and look at how a couple of challenges are addressed there. Okay, so addressing the challenges in the context of robotic swarms. The key question then becomes, why are we talking about robotic swarms at all? Right? What's so great about robotic swarms? So robotic swarms are resilient to failure. Usually, for example, we send a single robot up to Mars or to the moon, and if that particular robot fails, the entire mission fails. That is why we spend such a lot of time trying to make these robots really hardy and resilient to failure. We spend a lot of money on it, but we could make a lot of cheaper robots. And even if, let's say, 50% of them fail, we might still be able to complete the mission. So that's what the robotic swarm would help us do. We also obtain significant cost savings when we produce that scale, and that is something that we already know when we are looking at computers or any kind of mobile phones industries across the world. We also improve the efficiency of completing a task, right? So if we have got more number of robots and our mission is, for example, to map out the world, if we have a single robot, let's say Wally trying to clean up the entire world, or we've got 100,000 of them trying to clean up the entire world or map out the entire world, of course, those 100,000 of robots would be able to do the job faster. And there are a lot of applications for robotic swarms: infrastructure inspection, surveillance, search and rescue, exploration coverage. And these are just a few that I've mentioned over here. Okay, so let's see how we address the challenges of complex systems with regards to robotic swarms. So we'll look at challenge 2 over here, estimating the macro state. Swarming behavior is essentially what we are looking at in our research lab, can be modeled as having individual zones of repulsion, orientation, and attraction about an individual robot. So the robot is in the center. If another robot is really close and within the zone of repulsion, essentially the two robots will repel. If it's in the zone of orientation, whatever the orientation of my neighbors is, I will try to orient myself towards that. And the outer zone of attraction is essentially if there are agents or robots in that area, then I'll be attracted towards them. So the dynamics are essentially very simple. The first line that you see, xi, is basically the position dynamics, and that is simply kinematics. My position at the next time step is going to be my position right now, plus velocity times delta t. But it is this next equation, which is what is my heading going to be? That's kind of different. The first term on the right-hand side is essentially the average of the headings of all my neighbors. And let's see how this manifests. We have a video over here. So what we see is essentially the same kind of flocking behavior that we saw at the very beginning in the video. And this is arising just because of the simple rules of repulsion, orientation, and attraction that we have set up in this simulation. Let's have a look at this same thing being demonstrated in the lab as well. So we set up the hardware, we bought these Sphero robots, and these Sphero robots have LEDs on top of them, and we are using a visual system. Right now, the robots are just moving randomly. If they come within a specific zone of each other, they get oriented. So over here, you see some of the robots got oriented, but the other robot is going towards the north, and the robots are now moving together. They're essentially flocking, and now the final robot was close as well, and they essentially are swarming together, right? And again, it's using the simplest rule. If you're in my zone of orientation, I will change my heading to be same as the heading of the average heading of my neighbors. So this is something that we've demonstrated in simulation and in the lab. So we are able to recreate some kind of emergent dynamics. Now the key question becomes, how do we estimate or get a variable, a macro state estimation that describes this behavior? And for that, we have essentially started to look at the interaction complexity. So there is a network. On the right, you see two images, A and B. Let's say these are 5 robots, and they might be in different zones, and their communication network is essentially shown. And we use Shannon entropy, which essentially is being used in the context of coming up with the entropy of the network itself to figure out what the macro state is. And we do this with regards to 3 different networks. So on the left, you see the entire network, and we have broken this up into an attraction node graph, an orientation node graph, and a repulsion node graph. And what we are seeing is the entropy of each of these three different nodes or networks. And interestingly, we are able to identify the entropy. In the entropy space, we can see that there are three different kinds of behaviors that occur, which are similar to the three different kinds of behaviors we see in simulation and in our lab experiments, and that is swarming, flocking, and parallel flight. So we are able to use the network entropy as a macro state for describing how the swarm will behave based on its rules. And right now, we're also looking at thermodynamic analogs, essentially pressure and temperature, to figure out additional global scale properties of the robotic swarm. So that's our discussion on challenge 2. Let's have a look at top-down control of robotic swarms. This is an important problem because typically we have an understanding of what we want a group of robots to do, but we often do not know what the local rules should be. So instead of programming all the individual robots with different kinds of code, we just want to program with the same simple code, and the global behavior that we want should emerge out of those local simple rules. So this is not a new problem. People have looked at this before, and what we are going to cover in this specific section is the exploration coverage mission. Right? So you want to have a group of robots that goes out into the world, explores the area, and then basically covers the points of interest. So if there's something that is of interest, the robots would want to hang around there more than hanging around in an open field where nothing is happening. Right? The key distinguishing feature of our research over here is that the region of interest is essentially found by the robot itself rather than being human specified. So before we get into the details of our work, here's a simple animation that shows a frontier-based exploration. So the robot explores the area. It's exploring the world. It's going towards the areas it does not know anything about. And that is essentially being used to figure out what the world looks like. So people have tried to do this in the past. Multi-robot exploration coverage algorithms that currently exist have some limitations. Some of their trajectories can be redundant. Sometimes the algorithms do exploration but do not do coverage. Often the global density functions are user specified, so they're already given to all the robots, but that may not be a typical scenario. So you may not have knowledge about the world if you're having your robots go out and explore them, right? So that kind of becomes redundant. So what we try to do over here is essentially convert the existing algorithms. Instead of looking at occupancy distributions, we look at an entropy distribution, and we use adaptive grids, entropy-based adaptive grids, to improve the existing time-varying distribution control laws. So right now, on the left, we have a typical occupancy grid where we've got 3 obstacles, and we have a certain belief of whether there's an obstacle there or not. So in the center where you see the dark black circle, that's where we are really confident that there's an obstacle. So it's really likely that an obstacle is over here. But what the robots should be interested in is essentially areas where you do not have a lot of information. So what you should really be interested in is the areas where there's a lot of uncertainty. So you're not interested in areas in white, which you're pretty sure there is an obstacle. You're not interested in areas where there is an obstacle, or where it's very likely that there is an obstacle. What you're really interested in is the areas where you do not know whether there is an obstacle or not. So that's where the robot should go out and figure out whether there is an obstacle or not, right? And we do this in an adaptive entropy grid so that we are not using a lot of computation power. So what we have over here is essentially having different entropy split thresholds to figure out, basically this is like a blurry image, right? There is not a lot of information on the right side of the image, so there is no need to have really fine resolution there. There is a lot of uncertainty in the circles surrounding the obstacle, so we want to have fine resolution there, but everything else we don't really care about. So this basically, again, goes back to looking at the world at different spatial scales, different scales in space, and trying to figure out what is of interest to us, right? So with different split thresholds, we're able to see different kinds of resolution, and we want a fine resolution around the areas where there is uncertainty. So now let's just talk about a basic algorithm over here that kind of is used to explore the world. So the red dots on the right are the robots, and we use Voronoi regions, which are essentially perpendicular. If you look at the line joining the robots, you'll notice that the boundaries are essentially perpendicular bisectors of those lines joining the robots. So the Voronoi diagrams essentially create these regions in that specific fashion. So what we are looking for now is to have a uniform distribution across this entire square world. In order to do that, we have a simple algorithm called the Lloyd's algorithm, where the position is updated according to the error between the robot's current position, pi, and the location of the centroid, ci. So we'll just go through a small animation over here. So at the next time step, the robots move closer to their centroids, and because they have moved, the regions are again redefined based on where they are. The robots will move slightly closer to their centroids, the regions are redefined again, and finally, after a few time steps, they come to this configuration where the robots are now really on top of their centroid, so they're not moving anymore because the error pi minus ci is 0. And we have essentially a uniform distribution of robots across the world. Now, in this case, we had predetermined that we wanted them to be spread uniformly, but what we really want is essentially to have them figure out what the world looks like. So on the image on the right, you see that there's a lot of black, and we do not know what that region looks like. So we want the robots to explore that region and figure out where there is uncertainty and essentially evolve towards that. The actual dynamics are slightly different. You see that the first term on the right-hand side of the equation is the same as the previous one, but we have added additional terms that kind of look at the neighbors and figure out what the robots should do. So this is actually a video. I'll let it run. The robots are running and trying to figure out, exploring the world. And as they explore the world, they see that there is nothing on the right-hand side. So they say, okay, this is not of interest to us. We want to look at regions of uncertainty where there's high entropy. And they eventually head up towards that. And towards the end of the video, you'll see that all the robots are essentially just located on the left-hand side near the regions of high entropy. And everything on the right is basically just blank because there is nothing of interest there. Okay, so we are kind of extending this towards virtual reality because it's very difficult to run these experiments in the real world with a lot of drones. So what we are doing is essentially trying to run really fast experiments in the virtual world to get the right kind of controllers so that when we do deploy them into the real world, which we are beginning to do now, we do not have to do a lot of trial and error in the real world, which takes a lot more time than it does in the virtual world. So this is something that we're also working on, basically trying to control the robotic swarm using human gestures. Okay, so let's move on to additional challenges in the realm of connected autonomous vehicles, or essentially self-driving vehicles, right? And again, the question becomes...
Let me just quickly interrupt.
Yeah, sure.
And let the audience know. I think they are really, excited at what they're listening. I'm excited, learning a lot.
Okay.
And I just want the audience to know that please send in text messages as and when they come to your mind. Don't wait till the end. So keep sending in text messages and questions, and we'll collect them and address them at a later point. Okay? Go ahead, Kshitij.
Oh, okay, yeah. All right, so yeah, I guess this was a good breaking point to put in that comment.
Yeah.
Okay, so we talked about two different challenges. We talked about macro state estimation, and we talked about top-down control in the context of robotic swarms. Now we look at two other different kinds of challenges that we are focusing in with regards to complex systems in the realm of connected autonomous vehicles or self-driving vehicles. And then the question again becomes, why are we talking about connected autonomous vehicles? And we're talking about this because the traffic congestion costs are rising. And these are figures for the United States. And over the past few decades, the congestion cost has really skyrocketed. And this is something of significant concern, because there should be no reason that we're wasting hundreds of billions of dollars on just sitting in traffic, right? So this is a problem that we need to solve. So congestion costs are rising, but intelligent vehicles can potentially alleviate congestion, right? So if the vehicles can talk to one another and say, hey, I am stuck in a traffic jam, and they communicate that information to other people who are coming up behind them or other cars that are coming up behind them, they can maybe get rerouted or do some kind of control action so that the congestion is not propagated forward in time. So in order to do this, we essentially need to have some kind of model for figuring out whether there's a traffic jam or not. And there are lots of existing models. There are fluid flow based models, right? We've probably seen mechanical engineers would recognize this equation immediately. We've seen compressible fluid flow models, but these only model the traffic at the macroscopic scale, right? So these do not give us the information about what specific vehicles are doing. On the other hand, we have ordinary differential equations, or ODEs, that can model individual vehicles at the microscopic scale. So we have something like a car following model, which you see on the top left. X double dot is essentially acceleration. It is a function of the distance between cars, and a function of its own velocity and the relative velocity between cars. And we also have cellular automata-based models. And these are all very microscopic-based models. So they are useful, but we run into the same kind of problem that we talked about with the bird flock, right? 6 states, 1,000 birds, 6,000 state variables. It becomes extremely difficult to handle these in any meaningful way. In between these two, the self-organized jams that are formed are best addressed at these intermediate scales, right? I will not go into the details about this, except that we are now not looking at individual vehicles, and we are not looking at fluid flow. We are essentially looking at an intermediate scale, which can be defined as the size of the cluster. So that is what we did, and now we'll dive into how we're assessing these challenges. And I would just like to point out that one of this particular project is being funded by the NSF to figure out which is the intermediate scale that best suits the observability of these emergent dynamics. So at what scale should we be observing traffic flow so that we can best predict what might happen? So let's look at this in the context of the fourth challenge, which is the bottom-up synthesis of collective emergent behavior. So we know how humans drive, or we at least have some kind of model of how humans drive. Can we use those models and those interactions to figure out whether traffic congestion will happen, right? So to make things simplified, we start off with a closed ring road structure, which avoids open boundary conditions. So we don't have additional cars coming into the system. We don't have cars going out of the system. It's a closed ring road, but traffic jams still form. So we have removed all the confounding variables so that we can first get a good understanding of how this works in a closed system. The self-organized dynamics are studied in the context of a cluster size. So R over here represents the size of the traffic jam. And we use what is something that's known as the master equation to figure out how the probability distribution is changing over time. So if you look at the figure on the right, that green state R is, let's say, the state right now. And if vehicles leave the traffic jam or join the traffic jam, the state goes from state R to, let's say, R minus 1 or R plus 1. R minus 1 if a vehicle left the traffic jam, R plus 1 if a vehicle joined the traffic jam, and we can figure out what the probability distribution of these states is. And based on the rate at which vehicles join or the rate at which vehicles leave, we can figure out a master equation. So in order to do that, in order to figure out the transition probability of a vehicle joining a cluster or leaving a cluster, we have to revert back to the car following models, which describe the individual behavior of a car. Excuse me. So on the left, we have the acceleration of the n plus 1th car, which is a function of, if you look at the right-hand side, the term inside the brackets at the top is the velocity of that car. The term in the denominator is what is known as the space headway, which is the distance between the cars, between my car and the car in front of me. And on the right, extreme right, is the relative velocity of the cars. So the acceleration is a function of the velocity, the headway, and the relative velocity. And all of this is contingent on being multiplied by a driver sensitivity, right? And instead of having the sensitivity related to just a human sensitivity, what we are trying to do is, if the cars communicate with one another and they know that there is a large traffic jam in front of them, they could become more sensitive. So let's say you're driving on the road, and typically humans do not see 10, 20 cars in front of them. They can typically only see 1 or 2 or maybe 3 cars in front of them to figure out what to do. So if the connected vehicle or the self-driving vehicle can see 30 cars in front of them, they might use that to change their sensitivity so that they accelerate or decelerate sooner, so that they don't join the traffic jam that soon. So that's what we have over here. We modeled the sensitivity based on the cluster size n. So on the image on the right, you see the number of vehicles in a cluster on the x-axis and the driver sensitivity on the y-axis. So for a specific set of parameters, what we have over here is that if the number of vehicles in a traffic jam is small, then we don't change the sensitivity, and the entire traffic flow keeps behaving like it's made up of only human-driven vehicles. But if you are at the extreme right, if there's a really big traffic jam, then the sensitivity of the connected vehicle or the self-driving vehicle will change so that the traffic jam does not grow further. And we can do this at several different scales. So what you see over here is different sensitivities corresponding to B, which I don't think I mentioned. B is the slope of sensitivity to congestion. So over here, the blue line represents a really high sensitivity to congestion. The purple line on the extreme right represents a low sensitivity to congestion, so it does not respond even for large traffic jams. So if there are 300 vehicles stuck in a cluster, the purple line is still not responding. The algorithm is still not responding. So based on this, we can have an intuitive understanding of which of these algorithms will help us alleviate congestion. So if you're using parameter values like b equal to 0.01, which corresponds to the purple line, we should not expect behavior any different from what a human driven vehicle or human traffic with human-driven vehicles would look like, right? On the other hand, if we have something like blue, then we might see a significant difference. So what we see on the right now is the size of the traffic jam as a function of density. The purple shows the typical size of traffic jam as it grows with density for human-driven vehicles. But if we have the congestion-aware connected adaptive cruise control algorithm, the blue line with b equal to 0.6, what we see is even as the density rises, the size of the traffic jam remains really small. And it's only after the density reaches a really large value, 0.5 or beyond 0.5, that the traffic jam begins to form, right? So this shows that with our congestion-aware algorithm, we can reduce the size of the traffic jam in this scenario. So we can also talk about penetration rates, what percentage of vehicles in the traffic flow are actually CACC enabled. So if there are 100% of vehicles that are CACC enabled, so there are no human drivers, only computerized algorithms that are driving the cars, we see the most benefit. But even with 40% vehicles, we begin to see some kind of benefit, right? So this is useful even with moderate levels of penetration of these connected vehicle technologies. Okay, so we can talk about these different mixes, but we will now move on to challenge 5, which is the notion of influential subspaces in a connected autonomous vehicle. And I think this is one that everyone most easily relates with because it shows the it shows the level of control that a single individual can have on the traffic jam. So let's have a look at this. So the problem we are looking at is, give me a second. So the problem we are looking at is, can individual vehicles positively influence traffic flow or lead to faster traffic jam dissipation? And we'll talk about this in the context of connected vehicles, but we can also talk about it in connected vehicles does not necessarily mean autonomous vehicles. It just means that some information has been communicated from downstream of the traffic, so further ahead of you, to you, and you can use that information to do something. So we are assuming instantaneous communication, and we are saying that the vehicles have limited control options. So let's have a look at this. Let's say there's a traffic jam, right? You may have encountered this. Can you make this traffic jam go away? If you're really far away from the traffic jam, let's say you're in the next city next to you, which is 100 miles away, you do not expect your actions in the neighboring city to have an impact on the traffic jam right here, right? So this continues until a null horizon. There's a specific spatial boundary beyond which any actions you take have no impact on the traffic jam. If you are in this region too, where you're close to the traffic jam, but not too close, the actions you take can have an impact on the traffic jam. And we call this the influential subspace because it's the region within which you can influence the traffic jam. This extends up to the event horizon, which is the terminology we borrow from black holes. And if you're within the event horizon, you might take whatever action you want, but you will not be able to impact the state of the traffic jam. Okay. There's also region 4, which is beyond the traffic jam. You could take actions over here to negatively influence the traffic jam. For example, you just sit there and don't move at all. You'll make the traffic jam rise. But we are looking at positive influences over here. So we're looking at, let's say, the positive influential subspace. So if this vehicle, in the first vehicle in the jam, if it could communicate to vehicles in the influential subspace, then we could have a reduction in congestion. However, you cannot just broadcast your information to everyone because we have bandwidth limitations and there is a limit to how far you can transmit your packet. So what we essentially want is to have this car be able to transmit only to the vehicles which are within their influential subspaces so that they can influence. There's no point transmitting or wasting bandwidth on transmitting to vehicles that are in the green region or in the red region because they won't have any impact on traffic flow. So this is a very quick primer on the fundamental diagram of traffic flow, which in the considering the time, I will skip slightly. I will just explain the very basics. So over here, what you see, the dotted line is when the traffic jam vanishes and the traffic returns to a free flow state A, and J is the jam state. If the connected vehicle, second connected vehicle, which I've shown in yellow, is really close, it's not going to have an impact. If it's slightly behind, it still does not have an impact. If it's a little bit behind, further behind, it does have an impact. Well, right now it doesn't. If it's slightly behind, it has an impact because now in this state, you see that the traffic jam basically returns to free flow at a time earlier than any of the previous 3 cases I showed. So let me run this. Over here, no impact on the time taken to return to free flow. No impact on time taken to return to free flow. Again, no impact on time taken to return to free flow. But over here, we have returned to free flow sooner than we would have in other cases. Now, if you're in the green region, which is far away from the influential subspace, again, the original traffic jam still is dissipating at that initial time and it has no impact. So this way we can figure out the influential subspace. So if you're really close to the traffic jam, over here we see that the time taken to reach the desired macro state, which is free flow, so time taken to return to state A is really large and is the same as the time taken to return to free flow. If we are farther behind, we are able to get back to free flow faster, sooner. And if we are really far behind, then we are not able to change the time taken to return to free flow, which remains the same as the original time, which was the delay. So in this region, this green region, which is between the event horizon and the null horizon, that is the influential subspace corresponding to a specific time. Okay. Now we can look at how the event horizon or the influential subspace changes with respect to different locations. So over here, we've shown how it changes with respect to initial jam length. So if you've got a really big traffic jam or a small traffic jam, what does the event horizon look like? So we have, let's say the initial jam length, it's a kilometer long traffic jam, and the connected vehicle is somewhere over here. It is not going to have any impact. If it's really far out, behind in region 2, I think it was, it's not going to have an impact. But if it is in the influential subspace, the traffic flow will return to free flow sooner than 327 seconds, which is the contour line over there. So what we learn from this is that the communication has to happen over several kilometers in order to have an impact on traffic dynamics. And that is an important thing to know if we are building these DSRC or radio communication systems to basically improve traffic congestion, or if we have mobile cellular messages being sent to people, or if Google is doing something like this in order to communicate with specific vehicles based on their location, what kind of route they should take, right? This also helps us improve bandwidth utilization because if we know whom we should talk to, we only send the messages to them. Okay. So wrapping things up, I just want to step back and have a look at the grand challenges again. We're still looking at how to classify complex self-organizing systems into specific classes. That is still an ongoing area of research. We have done some research in terms of figuring out how to identify the locations or the state of the swarm. So we were doing this kind of macro state estimation in the entropy space of the network. And that is something we can use going forward to figure out what the next state of the, or do prediction of the swarm state. We looked at top-down agent control, where we said we had an understanding of what we wanted the robotic swarm to do, and we were trying to figure out what the local rules should be so that they explore and cover a region. We looked at bottom-up synthesis, where we knew the driving behaviors of individual humans or connected vehicles, and we were trying to see what kind of traffic jams happened because of these specific kinds of driving behaviors. We also looked at influential subspaces. So where can a specific agent have the most influence on the larger global emergent pattern, which we just saw moments ago. And we also looked at the direction of causality across scales. And I think this is a previous slide. So if you noticed the email address, that's an old address. I can give you the new email address, or you can reach out by looking at the Emergent Dynamics Control and Analytics Lab. You can search for it and you'll get you to the right email address. So these are the 6 challenges we are looking at right now. And hopefully you were able to learn something from this. Krishna, back to you.
Fascinating, Kshitij, fantastic, amazing. I'm just spellbound at all the analysis that you've done. Fact that you can use your systematic statistical analysis to understand what happens with birds and nature, and then use that type of understanding to actually predict and design systems for artificial intelligence and future of robotics and all kinds of technology in society. Fascinating. And I assume that these kinds of things also happen in social change when countries have revolutions and people have different views. And
yeah, they do. And that's my long-term plan, to look at that.
Yeah, social change. That's fantastic. So, yeah. Folks, okay, we got about 35 really fascinated people in the audience who have been listening, and I hope we'll have some questions. So just have a few minutes and to see if we can have a little conversation. So let's get the ball rolling. Anybody that wants to get this ball rolling, let's have a few questions, comments. I haven't seen any. I've seen one, I think, but let me see what that says, but please come in. So I think it's always a good opportunity to have interactions like this, to clarify, to discuss, to engage in these conversations. It's really fascinating. I think one of our participants is wondering if flying cars are in the horizon to overcome this traffic congestion. So yes, it's
So flying cars, so people are definitely working on it. Google has a program called Kitty Hawk, which was also the name of the place where the first aircraft flew, and I think they are definitely trying. Airbus has its Vahan program where they're trying to come up with personal flying cars, and there are companies, I think, in China called eHang that is working on it. So yeah, there are a lot of people trying to work on this congestion problem on a slightly different. They're saying instead of trying to solve congestion on the ground, let's just take to the air, and that will solve congestion. That also brings with it different safety issues.
Sure.
But yeah.
But what you've done is you've shown that it's possible to systematically do what nature does, and figure out ways to solve our problems without completely changing the technologies and so on. Okay, great. So another comment here, presentation was so good that it was so new to me to a webinar like this, and it'll definitely create interest to me in this field of research work. Thank you, he says. Congestion problem, next question, congestion problem is represented as a dynamically time-variant system, but how do you consider delays in the mathematical model? I'm not sure that's go ahead.
That's a very good question. Because some of the analysis that we did, we assumed that delays were absent, even with the connected, the influential subspaces example. We assumed that communication was instantaneous, and that helps us simplify the problem significantly to get some preliminary results. But delay is definitely a problem that we face, and any kind of delay typically leads to instabilities in the dynamics. But we have not delved into that in depth in our work right now. But that's a good question.
Good question, Srikanth, because I'll keep thinking along those directions and keep coming. Other questions, comments, and suggestions, interactions. Well, you can see that keep them coming. In the meantime, I'll put a little commercial in here for UMass Lowell, and then again see if there are any more questions. So put in some questions, and I'll take over the screen and do a little commercial. Okay, so for the institution where I get my salary from, right? So I got to. But it's not. It's more than that. I think UMass Lowell is a fantastic place. I have been here now since 1995, so it's almost more than almost 30 years. About 10 of those years was the Dean of Engineering, and so as you see here, then just a quick plug for UMass Lowell. I think it's not as well known as MIT and Harvard and other places, but I think we have faculty and research of the same caliber as some of the best institutions in the country, and that's why we want to let you know about it. And 18,000 students, not 18,000 students, and the number of students and the quality of the students has been increasing enormously in the last several years. We have more than 100 undergraduate, 42 masters, and 63 doctoral programs in 6 colleges, and 750 FTE faculty, 100 of them hired in the last 4 years. So there's been a growth, more $70 million in research expenditures, and the kind of exciting work that these kinds of research being done by our young dynamic and also more senior dynamic faculty members in various fields. It's an urban campus, and so our background has been working with industry a lot. And so our faculty are well connected to industry. Students get jobs and co-ops, and we got engineering programs in all these engineering areas, typical standard engineering areas, as well as energy engineering, energy management, plastics engineering, environmental studies, and so on. So our PhD and master's programs enrollments have increased enormously in the last 10 years. And again, that's a reflection of the quality and the demand for our programs. Research expenditures increase, and so there's lots of opportunities for potential collaborations and students from around the world to join our programs and be part of this exciting movement that is happening at UMass Lowell. A lot of the funding is from sources like NSF and DoD, and you can see that our background connection with industry is seen here. That 1/3 of our funding research funding comes from industry. So that's very significant. This is a lot of practical stuff is happening in our areas, and a lot of these companies are with us. They come regularly to help work on research and also hire our students. We have a very strong co-op program. Our strengths are in advanced materials. We have several centers in that area, in particular the flexible electronics, additive manufacturing, soldier protection support, medical device development, composites manufacturing. Under sensing and infrastructure monitoring, we have structural dynamics, acoustic systems lab, wind energy research group, bridge and rail infrastructure. Under systems engineering, we got Center for High Rate Manufacturing, advanced manufacturing, computing and machining lab, learning, and so this is that is the final slide there. We will have a next semester, next week, another one. Let me just quickly see if we have had any more. Come on, guys, questions. Anybody else? Comments, questions? Okay, I guess they're so fascinated that they haven't yet been able to figure out what question to ask. So that's good. I think it's been fantastic, Chitich, and one of the most impressive presentations that we've had so far. And I'm excited that you were able to give it, and I'm sure there's a lot of good future in the types of things that you're doing. And social changes, I would be particularly interested in that when you get to that, but that'll take a few years to get there. But I hadn't realized that there's such a systematic way to analyze these kinds of fairly random, chaotic events. And now that when the next time I look at a swarm of birds, I look at them from a different perspective, or a school of fish, whatever, or ants. Look at them from a different perspective and say, what can I learn from all these events that are happening that can maybe influence my behavior in trying to change. I'm as I'm passionate about changing the way teaching is happening, education is happening. So with 100 colleges all over India, so what can we do to think about the social dynamics of change in these institutions? Fascinating. Okay, thank you very much, Chitich, and have a good day. And I appreciate your spending the time with us and in preparing the slides and also preparing the presentation. And keep in touch. We'll collect information of who joined and send you the information. Okay.
All right. Thank you.
Yeah.